Assalamu alaikum guys, welcome back. This is Shafat Khan on your screen, and now in this lecture we are going to talk about giant covalent structures. In the previous lecture we compared giant covalent structures with the simple molecular structures, right? So now in this lecture we are going to talk about the giant covalent structures. Okay, giant covalent compounds, giant covalent structures. Okay, so as the name suggests, giant and then covalent. Okay, covalent means it contains covalent bonds, of course, and giant means there is a whole series, a giant series of covalent bonds in there. The structure is giant, meaning contains thousands of atoms in there. Okay, now these are basically those molecules which you've already covered in your O levels, but there are certain additional stuff that needs to be covered over here. So let's begin right now. All right, so first of all, the allotropes of carbon that you've done. There are two allotropes of carbon, diamond and graphite, that you've done in your O levels. These both of them have a giant covalent structure. Diamond, in fact, is the hardest known metal, having a melting point of around 2000 to 3000 degrees Celsius, and this is because of the many covalent bonds which are inside of it and the thousands of carbon atoms inside of it, which have to be overcome in order to break down in order to melt it down. Okay, carbon over here in the diamond has a tetrahedral structure, as covered in the previous lecture. In one of those lectures of shapes of molecules, I told you what tetrahedral was, right? Having 4 regions of electron densities, 4 covalent bonds are there, therefore it's tetrahedral, 4 single covalent bonds, and it's 109.5 degrees is the bond angle because it's tetrahedral, and tetrahedral is 109.5 degrees. And all the carbon atoms are bonded, meaning all the 4 electrons are also bonded. Carbon is tetravalent, right? And 4 electrons have been used in formation of bonds. That means no electron is free to move around, right? And if no electron is free to move around, that means I can say that there are no delocalized electrons present in diamond, right? If there are no delocalized electrons present in diamond, that actually means diamond is a poor conductor of electricity and heat. Okay, so this covers diamond, and its melting point is very high, and the force responsible for the melting point is covalent bonding, not the intermolecular van der Waals force. Okay, not the intermolecular instantaneous dipole induced dipole, but rather it's the covalent bond. So if you are asked to just to identify the force responsible for the high melting point, it's the covalent bonding, not the intermolecular forces in case of giant molecular structures. That intermolecular forces was responsible in simple covalent structures. Okay, and the hybridization of carbon can also be asked over here. So hybridization, how many regions of electron densities are there around this carbon atom over here? There are 4 regions of electron densities. 4 regions of electron densities means that there is a hybridization in which there are 4 orbitals mixed. So sp3 hybridization is the answer. Clear? So this finishes off diamond. Then coming to graphite. All right, so graphite is basically, in graphite, each carbon atom bonds to 3 other carbon atoms rather than being 4. Rather than being bonded to 4, it bonds to 3 other carbon atoms, forming a regular series of hexagons. Okay, hexagonal structure is made over here, a giant series of carbon atoms forming hexagonal rings. Okay, and hexagonal layers with space in between them. Now these layers on top and layers at the bottom, they have space in between them, and in between the different layers of carbon atoms, perpendicularly there are van der Waals forces, there are weak van der Waals forces going. So in graphite you've got both strong covalent bonds as well as the weak van der Waals forces. But if you are asked to determine the main force responsible for the high melting point of graphite, then of course it's going to be covalent bonding. Okay, not the intermolecular van der Waals forces. Now, what is the significance of the intermolecular van der Waals forces? The significance is that these forces and the space in between these molecules, they allow the graphite to act as a lubricant. Lubricant means a slippery material, a sliding material, right? So it can be used to reduce friction in vehicles or in other parts. So basically it's acting as a lubricant because the layers of graphite, when force is applied on them, they can slide over one another through the weak van der Waals forces. Okay, so this sliding makes it a lubricant, and that's because of the space in between the different layers, due to the weak van der Waals forces. If the van der Waals forces were strong, the layers would not have moved relative to one another. All right, then I told you in the beginning that each carbon atom is bonded to 3 other carbon atoms, right? That means the 4th electron is free for every atom in there. So per each electron there is 1 free electron. 1 free electron means that as many carbon atoms are in there, that many electrons will also be there, free, revolving here and there, moving around on top of the entire graphite layers, right? Meaning like this or like this. So there are electrons moving around here and there on different graphite layers. They are free, they are delocalized, they are free to move. This means that they can move to conduct electricity, because that's a property similar to metals. Remember, in metals we had a sea of delocalized electrons. You did it in O levels. So sea of delocalized electrons is responsible for the conduction of electricity. So over here there are electrons, they are moving around over the layers, which help the graphite to act as a good conductor. Therefore, graphite can also be used in making electrodes, okay, or in conducting electricity. The two major characteristics and the reason behind them: lubricant, spaces, and they can slide. Good electrical conductivity due to the delocalized electron per carbon atom, okay, because each carbon atom is bonded to 3 other carbon atoms. What's going to be the bond angle over here? And what's going to be the shape, and what's going to be the hybridization of this carbon atom? So basically the bond angle over here, if you look at it carefully, there are 3 covalent bonds, right? 3 single covalent bonds. This means that there are 3 regions of electron densities. 3 regions of electron densities mean that it's a planar molecule. Remember, planar molecule had 3 regions of electron densities. BCl3, we did the example of BCl3, had 3 bonds and no lone pairs, right? And if it's a planar molecule, then its bond angle is 120 degrees. And since there are 3 regions of electron densities, hybridization is also going to be sp2 hybridization. Why sp2? Because 3 means it will have a hybridization that contains 3 orbitals. So 1s and 2p. 1s and 2p. So 3 orbitals in there. Alright, so this completes graphite. Then coming to buckyball and graphene, these are 2 additional allotropes of carbon. Okay, oh sorry, I didn't tell you what allotropes actually mean. Allotropes are actually alternative forms of the same element, okay, and the examples are given over here. Now coming to the buckyball and graphene. Buckyball and graphene, these are not giant covalent structures, but rather they are simple molecular structures. They have low melting and boiling points. Buckyball has a structure similar to graphite, but the only difference is that graphite has hexagonal rings, right? Buckyball has 2 types of rings. It has pentagonal rings, meaning pentagons, and hexagons, both. So pentagons and hexagon, and it forms a sphere football like structure, okay? So it's a buckyball, and it has low melting and boiling point, and its formula is just C60, okay? It's C60, that's why it's simple covalent structure. Because graphite and diamond has carbon atoms in thousands, not in 60. Okay, C60, just 60 carbon atoms can form a buckyball. And what is graphene? Graphene, as the name is similar to graphite, it can also conduct electricity, by the way. If you take this buckyball and open it up, if you open up the buckyball, then if you get a plain sheet having hexagons and pentagons in it, that sheet is called graphene. And this graphene is a good conductor of electricity. Okay, as the name suggests, it is similar to graphite, right? Graphite is a good conductor, therefore graphene is also a good conductor. But remember guys, these are simple covalent. Their melting points and boiling points do not depend upon covalent bonding, rather it depends upon van der Waals forces, because they are simple covalent or simple molecular. Okay, then last and final of the giant covalent structure is silicon dioxide. And by the way, I added these 2 because I wanted to cover all the allotropes of carbon atom, out of which 2 are giant and the other 2 are simple molecular. Now coming to the last one, SiO2, you've done that in your O levels. Silicon dioxide, it's an acidic oxide, if you remember. Acidic oxide. You guys remember what acidic oxides are? Acidic oxides are basically those oxides that can react with bases to produce salts, right? That can neutralize bases are called acidic oxides. Now SiO2, and by the way, is insoluble in water, okay? Now it is also insoluble in water. Let me just write it down, because of course and by the way, SiO2 is the formula of sand, okay? Sand, it's the formula for sand, and sand of course doesn't dissolve in water, does it? No, it doesn't, okay? So, and now SiO2, in SiO2 each silicon atom is bonded to 4 other oxygen atoms, and each oxygen atom in turn is bonded to 2 silicon atoms, okay? Oxygen is bonded to 2 silicon atoms and silicon is bonded to 4 oxygen atoms. Now, bonded to 4 oxygen atoms, that means it's similar to carbon, right? 4 oxygen atoms mean similar to carbon. Carbon means it is a tetrahedral structure. So, silicon atom contains tetrahedral structure. Whereas, if it is tetrahedral, then the bond angle is going to be 109.5 degrees, and the oxygen over here is bonded to 2 silicon atoms. So, it has a structure similar to water, and water has a bond angle of around 104 and 105, right? So, I am going to call it 105 degrees. Okay? So this is the structure of silicon dioxide. Again, it is a giant covalent structure. It has high melting and boiling point due to the strong covalent bonds, due to a giant series of covalent bond. Okay, if you have to describe the structure of any of these diamond, graphite or silicon dioxide, the first line that you must mention in your answer is that they have a giant covalent structure. This should be the first line. Then secondly, they have thousands of molecules, or you should say that they have a giant series of covalent bonds linking many molecules together, many atoms together. Okay, so high energy is needed to overcome those bonds, therefore they have high melting and boiling point. Simple as that. And silicon dioxide also does not conduct electricity. Reason, because all the electrons have been used up in the formation of the structure, in the formation of the bonds basically. I'm not talking about the electrons of oxygen because they are not free. Again, they are lone pairs, but they cannot move around here and there. And this pretty much sums up all the giant covalent compounds, and this literally was a very important class. Okay, so make good notes of it and learn very well. Thank you.